In the last module, we were in the middle of derivation of conservation of momentum. So this was the Reynolds transport theorem application to the conservation of momentum, and there were two forces, that is surface forces, body forces. We said that there are pressure, normal, viscous stresses, and then gravity force, Coriolis force, centrifugal force are few of the body forces. So then we said that we did the two terms of the left hand side and we had arrived here, and remember we are deriving, let me remind you, we are deriving x momentum equation. I am bookkeeping the x momentum. Let me remind you, this is velocity into mass flow rate. Although I have written here as rho u square delta y by delta z, remember that should be visualized mentally as rho u delta y delta z, that is mass flow rate into velocity u, because that is the momentum in the x direction. So similarly, momentum in the y direction is mass flow rate in the y direction is rho v delta x delta z into what is the momentum it is carrying in the x direction, that is u into rho v delta x delta z. So we did that Taylor's expansion, we put all of that here, and we find that now these two terms get cancelled out, these two terms get cancelled out, and these two terms get cancelled out. So I am left with del of rho u squared by del x plus del of rho uv by del y plus del of rho uw by del z. Whole of this into delta x, delta y, delta z. You see, I have here one term, first term of my equation, that is del of rho u del t into delta x delta z. So what I will do is, I will write this LHS upon left hand side upon delta x delta y delta z is equal to the first term. What was the first term? We had del of rho u by del t, del of rho u by del t, and the next three terms which we had gotten here, that is del of rho u squared, rho uv and rho uw. Let me write that. So you have del of rho u squared upon del x plus del of rho v upon del y plus del of rho uw upon del z. So there is a small algebra which we need to do here. Now let me expand this, that is u of del rho by del t, that is I kept u constant and differentiated rho. Next term would be rho del u by del t, okay, plus here I will keep u constant and keep rho u varying. So that is I have taken u comma rho v, rho u. So you have u del rho u by del x plus rho u del u by del x. Similarly, u del rho v by del y plus rho v del u by del y plus u del rho w by del z plus rho w del u by del z. Correct? So let me just take few things I can take common. Let me take that. I can do it in a jiffy, but I don't want to go fast. So u, if I take common, del rho by del t plus del of rho u by del x plus del of rho v by del y plus del of rho w by del z plus rho I can take common in all of these terms. Rho if I take common, del u by del t plus u del u by del x plus v del u by del y plus w del u by del z. Please notice that what is this equation? This equation is nothing but my continuity equation. So that means by continuity equation, I had told you we are going to use this equation while deriving continuity equation. this vanishes, this is 0, this vanishes. So I am left out with, and also what is this term by the way? This is nothing but my total derivative of u, du by dt. So LHS upon delta x, delta y, delta z is equal to rho du by dt. So we are now through with the LHS. So if we recollect the x momentum equation, what is on the RHS? We have found out the LHS of this equation. Now what is left out is the forces which are acting. So let us do that bookkeeping of all the forces which are acting in the x direction. But before we do that, we need to get the feel of what all stresses are acting. So let me just write, let's draw a parallelepiped. Just draw along with me a parallelepiped. Okay. So what are the stresses acting on this plane? Outward, shear and shear. Okay. Similarly, on the other side of the x plane, so you have this direction and this direction. Okay. So they are acting on the x plane, right? And that is the direction of the normal to the plane on which the stress is acting. The normal is in the x direction, right? For this plane, the normal is in the x direction. So the first subscript is x, 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 because that is the x direction in which the outward normal vector is for this plane. So what is the direction? X direction. What is this direction of this stress? Y direction. What is the direction of this stress? Z direction. What about this? This is again x, y, z. So the first subscript denotes the direction of the normal to the plane on which the stress acts, and the second subscript denotes the direction of the stress. Okay. So similarly we can draw for the plane which is outward normal is in the y, that is sigma y, sigma y, sigma y, x, y, z, correct? So if you go to the slides, I have just drawn the same thing in the slides. If you just go to the slides for a minute, so you can just see that, you can see that this is xx, xy, xz, yx, yy, yz. Similarly, bottom also we can draw. I have just not drawn because it would make it clumsy. Let's get back to our notes. Now let's get back to our writing. Let's do the bookkeeping of the forces. Remember, right hand side sigma FCV was there. We are going to write what is sigma FCV. That is, I take a parallelepiped again. Please write along with me so that you will not miss out. So you have delta x, delta y, delta z. Now what is the force acting in the x direction? There is sigma xx in this direction. So you have sigma xx is acting over the area delta y, delta z. And what is it acting in this? This is again in this direction, left to right, outward. Sigma xx delta y delta z plus of del of sigma xx upon del x delta x delta y delta z. This is again by Taylor series expansion, just recollect that. Now let us write the shear stress and then come to pressure. The shear stress which is acting, if we just get back to my this, what are stresses I should take? Sigma xx will contribute for the x momentum and sigma yx will contribute for the x momentum. No other stresses are contributing for the x momentum. So I will take sigma yx, that is, this will be from right to left here and it would be from left to right on the top. This is same as what I had written here, okay. So you have sigma yx over the area delta x delta z, okay, and here this is sigma yx delta x delta z plus del of sigma yx upon del y delta y delta x delta z. Now which is the force which we have completed? Normal stresses and shear stresses. What is left out in the surface forces is pressure. Now you see, pressure I am taking left to right. Pressure always acts inwards and normal stresses always act outwards. This is one question students are going to ask. Why is pressure taken inwards? Stresses, normal stresses taking outwards is natural, we all understand, because we would like to take it to stretching, so that's why we take it outward. But why is pressure inwards? What is pressure? Let's get to what is pressure. What is pressure? Pressure is, to understand pressure, we should take, when will be the pressure is zero? If we take this room, when I take out all the molecules in this room, the pressure would become zero. Why? Because the pressure is the interaction of the molecules. Interaction of the molecules makes the pressure. So if there is no molecule, then there is no interaction, then there is no pressure. So if this is my elemental volume, fluid element, how would pressure act by other molecules? They would all come and hit this. So it will always be inward. So that is why pressure is inwards. Okay. So this is one question students are going to ask you. So we will have to be comfortable answering this, because pressure is the interaction of the molecules onto this fluid element. So you have P into delta y delta z, and this is P into delta y delta z plus of del P by del x delta x delta y delta z. Now if you just do this bookkeeping, so that is right hand side equal to, that is sigma FCV equal to this pressure, this force is acting from right to left. So according to our coordinate system, it's going to be negative. So minus sigma xx delta y delta z plus this force is acting left to right, so it has to be positive. So you have sigma xx delta y delta z plus del sigma xx upon del x delta x delta y delta z. Similarly for pressure, it is left to right, so it's going to be plus P delta y delta z minus P delta y delta z, because whole of this is acting from right to left. So minus of del P by del x delta x delta y delta z. Now what about the shear stress? This is from right to left, so this is going to be negative minus sigma yx delta x delta z plus sigma yx delta x delta z plus del sigma yx upon del y delta y delta x delta z. Okay, so plus body force Fx. I am taking Fx as the body force. This body force is per unit volume. Okay, so that is delta x delta y delta z. Now let me take RHS upon delta x delta y delta z is equal to, what will happen to these terms? This gets cancelled, this term will get cancelled with this term, this term will get cancelled with this term. So I am having minus del p by del x plus del sigma xx by del x plus del sigma yx by del y plus del sigma zx by del z. Z direction I did not intentionally write here because it's going to make it clumsy, but that's going to be on this surface. So del zx by sigma zx by del z plus fx. So which is actually equal to, if you recollect, what had we got for the right hand side? LHS upon delta x delta y delta z, that is rho du dt. So I can equate this rho du by dt. So this equation we have not arrived yet, because sigma xx, sigma yx, sigma zx is still in stresses only. We would like to write them in terms of velocities. So this is what is called as Cauchy's equation. It is still not Navier-Stokes equation, it is Cauchy equation. Now let us substitute what is, let's write the equations for sigma xx, yx, zx. I am going to write in this class directly, but in the next modules we are going to derive these equations what I am writing. That is sigma xx equal to 2 mu del u by del x minus 2 by 3 del dot v, and sigma yy equal to 2 mu del v by del y minus 2 by 3 del dot v. All constitutive equations I am writing, I may be using only few of them, but we are going to derive in the next few modules. 2 mu del w by del z minus 2 by 3 del dot v, and sigma xy is equal to sigma yx is equal to mu into del u by del y plus del v by del x. Sigma yz is equal to sigma zy is equal to mu into del v by del z plus del w by del y, and sigma zx is equal to sigma xz is equal to mu into del w by del x plus del u by del y. Please notice, all normal stresses are stretching, they are just stretching. That's why you have linear deformation, del u by del x, del v by del y, del w by del z. Okay, sigma zx is mu del w by del x plus del u by del z, correct, this is del z. So these, you see, these are cross velocity gradients. Cross velocity gradients mean angular deformation. We have seen in our previous modules. This is angular deformation. Now let me substitute this. Let us substitute this in our equation, that is rho, our equation is rho du by dt equal to minus del p by del x plus del sigma xx by del x plus del sigma yx by del y plus del sigma zx by del z plus fx. This is my equation. Let's substitute that. So rho du by dt is equal to minus del p by del x plus del by del x of 2 mu, that is this equation I am substituting, del u by del x minus 2 by 3 del dot v plus del by del y of sigma yx is given here, that is mu into del u by del y plus del v by del x plus del by del z of sigma zx is given to be mu into del w by del x plus del u by del z plus fx. Okay, so we need to do minor algebra, 1 or 2 steps, but we will be there. So now we can see everything in velocities. So rho du by dt is equal to minus del p by del x plus, I am assuming the viscosity is constant, so I am pulling out, so mu, there is 2 del squared u by del x squared, I am writing only one, that is del squared u by del x squared, okay. Another term we will keep it like that, plus here if you come to the first term here, you have mu del squared u by del y squared, then first term of this is this term del squared u by del z squared, del squared u by del z squared. So this term is over, this term is over, one of this term is over, okay. So now what is left out is plus del by del x of del by del x of del by del x of one of these term is left out, so mu del u by del x, correct, plus you see here del squared v by del y del x, but I can, it does not matter in which order I differentiate, so I can interchange this x and y, so I can write mu of, that is del v by del y, correct. I have just interchanged this x and y. Similarly, I will interchange this z and x, so I get del w by del z. What is left out now? Minus of del by del x of, here actually I have missed out mu here, please write down, I am sorry about that, mu is missed out, so mu is here, okay. So you get minus of 2 by 3, minus is there, so 2 by 3 mu of del dot v. So what is this, by the way? This is nothing but my del dot v. So this is 1 minus of 2 by 3, that's going to be 1 by 3 mu del dot v. Let's do that. So what do I get is rho du by dt is equal to minus del p by del x plus mu del squared u by del x squared plus del squared u by del y squared plus del squared u by del z squared plus del by del x of mu by 3, that is, as I said, 1 minus 2 by 3 is 1 minus 2 by 3 is 1 by 3. So you get mu by 3 del dot v plus fx. So this is what we derived as the x momentum equation. So we can write similarly y momentum equation. So rho dv by dt is equal to minus del p by del y plus mu del squared v by del x squared plus del squared v by del y squared plus del squared v by del z squared plus del by del y of mu by 3 del dot v plus fy. Similarly, rho dw by dt is equal to minus del p by del y plus mu del squared w by del x squared plus del squared w by del y squared plus del squared w by del z squared plus del by del z of mu by 3 del dot v plus fz. So we have successfully derived the x momentum equation, y momentum equation and the z momentum equation. Okay. So if we combine all of this and write in vectorial form, so we can write this as rho dv by dt is equal to minus del p plus mu del squared v plus mu by 3 del of del dot v. Please notice I have pulled out viscosity, I have already assumed viscosity is constant, plus f. So these equations are called Navier-Stokes equations because they were independently derived by Navier and Stokes. That's why we call them as Navier-Stokes equations. Now let's write some reduced forms of these equations. That is, if we reduce, this is my Navier-Stokes equation. Now if I write for viscous, this is for general, this is for viscous compressible fluids, because I have not made any assumptions. Only assumption I have made is viscosity is constant. Correct? Now if I write this for incompressible fluids, what is that for incompressible fluids? We know that for incompressible fluids del dot v is going to be equal to 0. So my equation reduces to rho dv by dt is equal to minus del p plus mu del squared v plus f. Now let me write for inviscid flow, inviscid, incompressible, fluids. So what will you get? So this viscous term will vanish. So you are going to get rho dv by dt is equal to minus del p plus f. So this is nothing but my Euler's equation, but you can't see it directly the way we write it. So let us do little algebra. So just to get our regular Bernoulli equation what we write, we would like to see how we can get that. So that is rho, if I expand this rho dv by dt, what will I get? Rho del u by del t plus u del u by del x plus v del u by del y plus w del u by del z is equal to minus del p by del x minus rho g. That is, I have taken body force from top to bottom, that is, it is acting downwards. So you have a streamline in this, this is my streamline and this is my delta z. Okay. So and let's say this is sine theta. Okay. So if I were to just write this equation along a streamline, if I were to write this equation along a streamline, if I were to write this equation along a streamline, what is that for Bernoulli equation? There are three assumptions. What? Number one, it is steady, incompressible and inviscid. Correct? Inviscid I have already taken, viscous terms I have already removed. Steady means del u by del t is going to go away. Okay. Along a streamline means if I take s, s is the direction of the streamline. So this term will vanish, this term will vanish. I will be ending up with rho u del u by del s is equal to minus del p by del s, that is along a streamline. Now minus rho g. Now this becomes actually rho g, I have to take this as this is delta S. It is to be acting on the this component in the y direction. So that means I will get delta Z by delta S. Okay, that is sine theta. I will have to take g sine theta. So sine theta is nothing but delta Z by delta S, if you want to remember sine theta equal to delta Z by delta S. So you have rho g del Z by del S. So let me multiply throughout this equation with ds. So rho u del u by del S ds equal to minus del p by del S ds minus rho g del Z by del S ds. So what will I get? This is nothing but rho u du equal to minus dp minus rho g dz. Okay. So if I integrate this, what will I get? Rho u squared by 2 equal to p minus rho gz plus constant. So if I divide throughout plus constant, let's say C1. If I divide throughout by u and rearrange, I get p by rho plus u squared by 2 plus gz equal to constant. This is my regular Bernoulli equation. Okay. In this module, so we have derived momentum equation. So let us summarize in the next module this momentum equation and get started with the energy equation. Thank you.